The ways in which we use technology will create substance. The ways by which we use it.
Hello and welcome to another interview on energynews.biz. My name is Arnes Biogradlia and my guest today is Dr. S.A. Sheriff, a distinguished professor of mechanical and aerospace engineering at the University of Florida, who has made a significant contributions to the field. He holds esteemed fellowships and has demonstrated his expertise through leadership roles in many professional organizations. Dr. Sheriff, welcome.
Thank you very much.
For the beginning, tell me, who is S.A. Sheriff?
Yes, well, thank you very much for hosting me today. It's my pleasure to be with you. I started my academic career a long time ago. I got my doctorate. It was predominantly in heat transfer and fluid mechanics. And then I started my academic career at Northern Illinois University, about 60 miles west of Chicago. 3 years there, and then I moved to the University of Miami, where I met Professor Nejat Veziroglu, who was an extremely supportive and helpful colleague who took me under his wing, and I was much younger at the time, and we started on hydrogen energy back in the time when there was not a whole lot of talk about hydrogen energy. This was back in the 1980s, and I was very fortunate to have had my path crisscross with Professor Veziroglu's path. We were involved in I believe, the first renewable hydrogen funded research grant from the Department of Energy, and in the late 1980s. There were 4 universities involved. The University of Miami was one of the 4. University of Hawaii in Manoa, Florida Solar Energy Center in Cocoa Beach, Florida, and Texas A&M University in College Station, Texas. And the Solar Energy Research Institute, which was the predecessor of the National Renewable Energy Laboratory today. It's one of the laboratories of the Department of Energy. At the time, it was called the Solar Energy Research Institute, and they were, in fact, they operated as a project monitor. So we ran that program for several years. There were many tasks involved. Of course, Dr. Veziroglu was the PI on the University of Miami's portion of the grant, and within the University of Miami itself, we had 4 tasks. One of the tasks was hydrogen liquefaction and storage, which I was in charge of. We had other tasks that involved hydrogen safety and the hydrogen energy system task that we had. There were four major tasks that we were in charge of, and liquid hydrogen was the area that I was in charge of. And I was very fortunate. I hired at least 4 research assistants that worked day and night, and we produced a lot of good work at the time. One of the students that I had, she ended up getting a PhD in hydrogen energy. In fact, she worked on magnetic hydrogen liquefaction, which was at the time a very new area of research. Magnetic hydrogen liquefaction. There was a company in Wisconsin, Madison, Wisconsin, by the name of Astronautics Corporation of America, and they had the Energy Technology Center within that company. They were working on room temperature magnetic liquefiers, and later on room temperature magnetic refrigerators. Professor Carl Zim and Professor Tony De Gregoria were involved. And at the time, Professor Barclay, who later moved on to the University of Victoria, I believe the University of British Columbia in Victoria, he took, and then later on and back in the industry, he was a big shaker and mover in the magnetic liquefaction of hydrogen component of it. He has a lot of key publications in that area, and one of his PhD students later on became a professor and took on the laboratory that he established in Victoria, British Columbia.
I have quite a few questions on liquefaction, but let's start with this one. How do advancements in hydrogen production technologies impact the scalability and efficiency of hydrogen energy systems?
Right now, there's a lot of people working on many aspects of the hydrogen energy system, if we can call that, to encompass everything that is under the umbrella of hydrogen energy. And it ranges from production to storage to transportation and handling to safety and codes and standards and many other areas within the realm of making that the new energy system. The scalability is really a function. It's a function of a lot of things, but it's a function predominantly of the uh, the cost. If we can make this whatever system we produce affordable, there will be more people that buy into it, and therefore the cost will go further down. So the scalability is not an issue as far as the technology know-how. We know how to do things. It's a question of does it make economical sense to do it? It's not a question. It has never been a question of do we know how to do it. Even from the days of back in the 1970s, when like someone like Professor Michaels at the University of Miami, when he built 19 hydrogen prototype engines for Ford Motor Company, for example. He worked with Toyota. He worked with Nissan, and he knows exactly how to build a hydrogen internal combustion engine. It's a question of does it make sense? And there were cars and buses that actually were built on using that technology. And of course, the same thing can be said about fuel cells, hydrogen fuel cells, and other areas. So just to answer your question in a shorter way, the scalability is a non-issue as far as technology know-how. It's a question of economics.
How can hydrogen storage technologies be improved to address energy density, safety, and cost effectiveness?
Well, hydrogen energy has a lot of advantages. One of them being that the carbon footprint is basically zero. When you combust hydrogen, you produce water vapor. There are traces of nitrogen oxides, but those are minor pollutants. So the big advantage of hydrogen is that it is clean. The difficulty with hydrogen is that there's no atomic hydrogen present by itself. It's not available in nature. It is always part of other things. Like in hydrocarbon, for example, there's hydrogen, methane, and all that. Then you have the hydrogen that is abundance in water, because H2O, water is there's quite a water present. But extracting the hydrogen molecule from the water molecule becomes a problem. So the productivity, to be able to produce it is the biggest challenge. And the second biggest challenge is once you produce it, what do you do with it? Hydrogen is a very light element. It has a tendency to escape as a gas. It's comfortable being in the gaseous phase. In order for you to convert it into a more controllable a mode of storage, like liquid or solid for that matter, you're going to have to perform a huge amount of of cooling, which you have to get it down to minus 253 degrees Celsius. For example, the boiling point of hydrogen is to 20.7 Kelvin. So it's a very low temperature that requires gigantic refrigeration, and of course you have to insulate the storage tank, and you have to keep at low temperatures or higher pressures, or a combination of both. But the biggest problem with hydrogen also is that there are two types of hydrogen that exist in nature. There's something called ortho hydrogen and something called para hydrogen. And the normal hydrogen at normal temperatures and pressure, there's 75% of it is ortho hydrogen and 25% of it is para hydrogen. The hydrogen brand of hydrogen is an unstable form of hydrogen. It's less stable than para hydrogen. And eventually, over time, if you leave normal hydrogen present for a long time, it will eventually convert. All of it will convert into para hydrogen. It takes a long time to do that. But as it moves from ortho hydrogen to para hydrogen, it releases heat. It's an exothermic reaction that results in a release of heat, and that heat is used to vaporize the hydrogen, the liquid hydrogen that's present, which makes it all the more likely to escape. If you put, for example, liquid hydrogen in your car as like fuel, if it's not in para hydrogen form, you need to have it in 98%, 99% para hydrogen if you have any chance of keeping most of it in your tank over the next 3 or 4 days. So what they do is as they liquefy hydrogen, they use catalytic converters to speed up the process of conversion from ortho to para, and then remove the heat that is released because of the conversion reaction. You have to take that heat out in order to minimize the boil off. So there's a lot of challenges. I mentioned the production challenge, the storage challenge, and of course, eventually you get into the safety challenge. But the safety challenge, I think, is the least of the problems that we have, because as Dr. Michael Bain will tell you, we did extensive studies on hydrogen safety, and one of the good things about hydrogen is that it's so light that it actually, if it gets released, it can, if there is a path, escape path to it, it will escape. For example, in the kitchen, if you're using hydrogen in the house, and what they do is they have a vent in the top in the kitchen, and as soon as hydrogen gets released, it actually goes up and escapes the house. So that the same thing if you're driving a car that has a tank of hydrogen, liquid hydrogen, for example. If you ever get into a collision, the good news is that the hydrogen will actually go up. It will not kill you. You may get killed from the collision itself, but you're not going to get killed from the fire that may result as a consequence, because the ball of fire will just go up, and it will not, unlike methane or propane. For example, propane is a heavier element, and propane has a tendency to linger in the lower layers of the air. There was a muffler shop in Dade County back many years ago that had a propane tank that leaked, and the next morning when the technician came and switched the light on, the spark, there was enough methane that congregated in the lower layers, and it kept building up, and when the spark just from the light switch, it destroyed the whole shop. That would not have happened in a hydrogen release, because if you have like a vent in the ceiling, the hydrogen would have actually escaped. The propane will not have escaped. So unlike what many people think about hydrogen as being unsafe, it's actually much safer than many other things that we use, including propane and other, even natural gas.
So with hydrogen, does it pay off pursuing the hydrogen economy with all the challenges that it has?
That is a fantastic question, and I think that is where some of the critics would come in. And back in the days, Professor Frank Reith, the late Professor Frank Reith, who was a giant in energy, so energy in particular. He had many books published by CRC Press and Taylor and Francis later on when they became Taylor and Francis. And he invited me to write book chapters on hydrogen energy. And in one of my presentations in a conference, and he was sitting in the front row, and he said, I'm one of the most I'm one of the critics of hydrogen energy. I don't believe that it will actually, that the energy that you get out of hydrogen is more than the energy that you put in to produce it. And he, I'm paraphrasing what he said, but he said, but I'm a professor. He said about himself, but I am a professor, and my job is to produce the knowledge so that people can read it and then can make up their own minds. And as a consequence, he invited me to write many book chapters about hydrogen energy in many of his books, even though he himself does not believe, at least at the time, did not believe in it. Now, judging from where things are moving to in the United States today, where the Department of Energy is, wholeheartedly behind hydrogen as far as being a viable energy system that they would move into. They created the Hydrogen and Fuel Cell Technologies Office several years ago. They are funding a lot of research on hydrogen energy. There's a hydrogen shot, which now they're trying to, they call it the hydrogen shot, which essentially is that you bring down the cost of hydrogen from $5 per kilogram to $1 per kilogram in 1 decade. So they call it $1 kilogram and 1 decade. So you want to bring down the cost by the end of this decade. They want to make it where $1 per kilogram is what it would cost to produce hydrogen. So the Secretary of Energy has made many presentations about that, the total commitment. So I would have to say, given, again, as an observer, my job as a professor here is not, I don't want to judge anything, but I'm a careful observer of events, and I can tell you that that with thousands of researchers working worldwide, compared to what was the case in the late 1980s, the International Journal of Hydrogen Energy is an excellent example of how the growth has been more than exponential, for that matter. Last year it was 100 issues. They published 100 issues per year. The year before they published also 100 issues, but their issues were large. I mean, we're talking 45,000 pages per year of hydrogen research that is being produced. I would have a tendency to not to think that all these people can't be wrong. The Department of Energy can't be wrong. I mean, there's always a possibility that we're all on the wrong track, and there is a bandwagon effect. There is that possibility. I have to say. I mean, I'm not saying 100%, but I would like to believe that we have finally figured out that this is the only way to go. There was a time when the Department of Energy was talking about all options are on the table. If you go back 10 years ago, for example, 15 years ago, if you ask anybody within the Department of Energy as to where are we going, what is the new energy system, they will say all of the above. There's the all of the above option, which is right now we're going to work on all of these different things and then let them sort themselves out, so to speak.
So, from your point of view, what are the current infrastructure requirements and investments needed for scaling up hydrogen production and distribution and utilization?
I would say there's several things, but the most important perhaps is if you go to the transportation sector, for example, in the transportation sector, if we're going to go with a hydrogen fuel cell, which I believe is the more viable option than electric cars or hybrid electric cars, the batteries are going to be a problem. The batteries consume, they produce a carbon footprint at the production stage They don't produce it when you're running the car, but they do produce it at the production stage. And they also have to be disposed of. And also the battery materials, some of the battery materials are limited in existence on Earth, meaning that over a long period of time, you will run out of certain elements of what constitutes a battery or what forms a battery. So I do not believe personally that the battery or the hybrid cars or the electric cars are the long-term solution. They may be a good interim solution for now. I believe the long-term solution in the transportation sector is a hydrogen fuel cell, whereby you are you have a tank of oxygen and a tank of hydrogen, and you mix them up together. You produce electricity. That is the opposite of the electrolysis process, where you run an electric current in a tank of water, and you collect the hydrogen and the oxygen on the cathode and the anode. Okay, that is the electrolysis, and that is a very well developed technology. We know how to do it. The question is, where do you get the electricity from? Well, electricity, in my opinion, should come from solar energy. Yeah, now, with the price of photovoltaic cells coming down by a big amount, it is now finally getting to the point where it is able to compete, where you can produce electricity from solar energy using photovoltaic cells. Take that electricity, and use it to electrolyze water, seawater, for example. You can take, don't go with fresh water or potable water. The supplies of that are limited. But if we go to seawater and figure out a way to overcome the issues with corrosion and all that, you can use that to electrolyze seawater and produce hydrogen and oxygen, and that hydrogen can be stored maybe in gaseous form, and eventually, if you're going to sell it at the gas pump, or in this case it would be a hydrogen pump, essentially. It may have to be in liquid form. It may be if you're gonna fill up a tank, you need it liquid. Okay, so liquid, that's a challenge, but again, with all the problems I mentioned about liquid storage, we have to find a way to overcome that, and there are people working on solving the Ortho Para conversion problem, and the boil off losses, and the heat leak, and the sloshing and the flashing. All of these are issues that are within, when you transport, for example, if you have a truck uh, uh, transporting liquid hydrogen, and the truck is going to come and stop at the traffic lights. The stoppage and starting and stoppage is going to make the liquid hydrogen inside the tank move back and forth. As it hits the front and the back, the kinetic energy will be converted into thermal energy, and it will actually result in boil off. It will be heat that is going to result in converting liquid hydrogen into gaseous hydrogen. So there are issues, but I'm saying that I can foresee, fast forward in time, and I can see that if we were to get the price of electricity from photovoltaic cells low enough, we can use that electricity to electrolyze seawater, get a lot of that in the form of hydrogen, store it, and then use it into the new infrastructure that we're going to have to build, so that you will have instead of a gasoline station everywhere, you will have a hydrogen fueling station everywhere. So that is going to take time to just convert the infrastructure. Uh, the good news is that you could use some of the natural gas pipelines. You could with some modifications, you can regarding embrittlement and all that, because they're not fully compatible. But you could conceivably create gas hydrogen transmission lines, similar to the natural gas transmission lines across the whole country. So again, there's a lot of issues, but we have to work on each and every one of them.
You mentioned liquefaction. Have the economic analysis considered all the possible variables influencing the cost of hydrogen liquefaction?
We did, our team back many years ago, we did several studies on economics. there are issues. Again, at the time we did the work, there is one of the papers, I believe, that we published in the International Journal of Hydrogen Energy, Economics of Hydrogen Liquefaction, and we looked at different liquefiers and different methods of liquefaction, and we did some cost analysis and all that. And we can need to update that because, of course, the economics of it now is different. But yes, the problem is it can be done. It can be done. It can be made economical. And again, was the production. If you can produce hydrogen at $1 per kilogram, that is going to be a good chunk of the total cost, because liquefying hydrogen and keeping it liquid, even though it requires additional energy, when combined, if you have a lot of cost to produce and a lot of cost to store and a lot of cost to transport, then you're fighting on 3 fronts or 4 fronts, right? So what we need is just try to work on each aspect of it. The production part, I think we're making good progress on that. The storage part, we're making good progress on that as well. Have we gotten there yet? Not quite, but we are working towards that. There's also the storage with metal hydrides, which is another form of mode of storage that the Department of Energy is very interested in, and they have put some targets for storage density of hydrogen in metal hydrides. So that's, you don't have to necessarily go with liquid. Even in the transportation sector, you could have a gaseous storage tank. It doesn't have to be in liquid form, but of course you will not be able to have as much hydrogen on the car as a liquid, and if it was in liquid form. And of course the issue of how high the pressure of the gas of the tank should be. You're looking at, because the higher the pressure, the more risk you take in, just in case there is a collision, for example. Okay, so you can also the cost of the storage vessel. If it's a high pressure, it's going to be heavier and it's going to be bigger, and it's going to be, and on the car, the consumption of fuel is going to be higher if you have a heavier storage tank, for example. There's a lot of issues there.
Can hydrogen liquefaction systems operation and maintenance costs be optimized further?
Yes, the costs can definitely be optimized further as far as liquefaction and operation for hydrogen. In fact, I can say everything within the hydrogen, the bigger picture of a hydrogen economy can still be fine tuned, even though we've made a huge progress over the past 30 years or so. If you go back from the late 1980s until today, we are light years ahead of where we were at the time. But research shall continue and should continue to fine tune things and get them more optimized and more cost effective. And also we have room to improve. We still have a big room for additional fine tuning and optimization. Yes.
So what are the specific technological advancements that can help actually reduce the cost of liquefaction?
Well, depending on what you use, what liquefaction method you use, the answer will be different. Okay, so for example, if you use magnetic liquefaction or hybrid, what they call hybrid liquefiers, where they use magnetic along with, let us say, Collins cycle liquefaction type of system, which is a more conventional type. The answer to your question would be different. But the main thing was liquefaction. The main thing was liquefaction is how to reduce the energy that is used to re-liquefy the hydrogen if it gets vaporized. So what you want to do is have what we call a preventive approach to prevent the liquid hydrogen from becoming vapor hydrogen or gaseous hydrogen, and then re-liquefying it. Okay, you wanna do what they call a preventive approach instead of a cure approach. the second issue is uh, how to keep it stored as liquid for a long time without spending a lot of money on the cooling component of it. Okay, so you're going to have to find what they do. For example, is they have excellent insulation systems. The tank. If you go, for example, to the Kennedy Space Center, you'll see this big spherical container that had H2 on it. The shape of the storage tank is important, and I believe that the spherical shape is the best among all of the different options, like cylindrical containers and others. So the cell containers are better. There also, if you were to have the walls of that container, if you were to have, it could be vacuum jacketed insulation, for example, where you have a vacuum layer between the inside wall of the tank and the outside wall of the tank. So you'll have a wall that's in physical touch with the liquid, and then you have uh, a vacuum jacket, and then you have the outside layer. Okay, so we also have radiation shields. You could use radiation shields to minimize radiation heat transfer. There's a lot of things you can do from a heat transfer perspective to actually reduce the heat losses or the heat gains from the outside, so that you don't fight the fight of the heat transfer part is a big fight. The boil off losses due to Ortho Para conversion, I believe, is easy to fix, because we will convert it all into para. At the time we liquefy, we use catalytic converters so that we can produce, let's say, 98% of the hydrogen would be in para hydrogen mode. So that is an essential part, and I think it's pretty straightforward to fix. The sloshing and flashing, if you, for example, if you're moving in a truck and it's the liquid goes back and forth and hits the walls and all that. I don't have a quick fix for that. I mean, that's going to be there no matter what you do. The flashing, which happens when you move hydrogen, transport liquid hydrogen from one tank to another tank. In order to do that, you're going to have to make the pressure of the source where the hydrogen is coming from higher than the pressure of where the hydrogen is going. And so that process from going from a higher pressure to a lower pressure is going to result in flashing of some of the liquid hydrogen, because when you reduce the pressure, the molecules are freer to the intermolecular distances become large, and they have more tendency to become gaseous instead of liquid. So the flashing problem is there, but it's not huge. And it only happens when you transport hydrogen from one tank to another tank. And so there are challenges, but again, there are many people, the many great minds that are there from all over the globe that are working on different fixes for different things. I think we're going to find a solution that would work, and we have no choice but to find a solution that works, because we're going to run out of fossil fuels one way or the other sooner or later.
Since you mentioned it, is there an ongoing research on making hydrogen liquefaction more cost-effective and sustainable?
I'm sure there is. I am not aware of anything off the top of my head right now. Uh, uh, I myself, I have a PhD student that is working on liquid hydrogen storage in microgravity or zero gravity conditions. That's going to be his PhD research. We're still in the early stages of things. Uh, I cannot think of other people off the top of my head, but I know that they're out there trying to make the liquefaction uh, more viable and more likely to succeed.
Dr. Sheriff, thank you for being my guest today.
Thank you very much for having me.